Hello, and welcome to the CCNA Routing and Switching course offered by Simplilearn. The previous lesson focused on networking models. This second lesson will deal with network topologies and Ethernet. Let us begin with the objectives of this lesson in the next slide. By the end of this lesson, you will be able to identify network topologies, describe the Cisco Hierarchical Network Model, explain Ethernet technologies at Layer 1 and Layer 2. Describe the Ethernet Layer 2 frame. Explain full and half duplex and CSMA/CD. We will discuss network topology in the next slide. As shown in the image on the slide, network topology deals with how devices are connected. As shown in the image on the slide, different devices in finance, IT Level 1, IT Level 2, and marketing are connected through a network. This is dependent on the technology available. Network topology is categorized into few types. We will be looking into them one by one in the following slides. Let us list the various types of network topologies. They are point-to-point, bus, ring, star, full mesh, and partial mesh topology. We will discuss each of these topologies in detail in the following slides. Let us begin with the point-to-point topology in the following slide. As shown in the image on the slide, in a point-to-point topology, only two devices are connected to each other through the medium. As shown in the image on the slide, device A is connected to device B and vice versa. This is typical in wide area network WAN connections. Let us move on to the next type, that is, bus topology. The image on the slide depicts that all devices are attached to a single cable in a bus topology. This was used for token ring networks. As shown in the image on the slide, devices A, B, and C are attached to a cable. Note that in a bus, all the attached devices receive all the data, whether it is addressed to them or not. This results in a very busy network. We will move on to the ring topology in the next slide. As seen in the image on the slide, in a ring topology, each device is attached to only one other device on either side, forming a ring network. As shown in the image, device A is connected to device B and device D. Similarly, device A and device C are connected to either side of device D, and so on. Nowadays, this is often used with servers. Moving on, let us discuss star topology in the next slide. The image on the slide depicts in a star topology, multiple devices are connected to a central device or hub. If one centrally located device fails, all devices connected along that branch lose connectivity. There are no backup devices. As shown in the image on the slide, devices A, B, C, and D are connected to a hub, that is, switch. If there is a failure in the switch, all the connected devices will be affected. This is the most widespread topology in networks today. In the next slide, we will look into the full mesh topology. In a full mesh topology, all the devices are interconnected. There are many backup paths from one device to another. Full mesh topology is expensive and difficult to implement. The image on the slide depicts full mesh topology. The devices, that is, device A, device B, etc., are all interconnected, which provides the scope of backup paths. The next and the last topology is partial mesh topology. The image on the slide shows a modified switch block. In a partial mesh topology, some of the full mesh connections are dropped. This makes it less expensive and easier to implement. A switch block is the recommended topology for implementing additions to the network. As shown in the image, few of the devices are interconnected, similar to full mesh topology, but the rest are connected to one or two devices. Based on the characteristics of these topologies, Cisco developed the Hierarchical Network Model that makes network design more systematic. Let us discuss this in detail in the next slide. The Hierarchical Network Model can help accomplish the goals of a network. To understand the Hierarchical Network Model, you would first need to determine the qualities a network should contain. Networks should be modular, resilient, and flexible. Modular implies adding to the network does not require redesigning. Resilient means the network can recover quickly from a node failure. Flexible implies modification of network is faster and easier. In the next slide, let us continue discussing hierarchical network modeling. The image on the slide depicts how each layer fits together in the network. As discussed, the hierarchical model was developed based on the characteristics of various network topologies. It has 3 layers: core, distribution, and access. There are 2 types of connections that link the devices. They are Layer 2 and Layer 3 connections. As depicted in the image, both these connections are present between the devices. Note the Layer 3 connections end at the distribution layer. Below that, all connections are Layer 2. The rest of the connections are Layer 3. In the image, the router connects to a remote network. This is a Layer 3 connection. Distribution and core layers are linked through Layer 3 connections. The switches in both these layers are multi-layer switches or MLSs. These can do Layer 3 routing and Layer 2 forwarding. Let us discuss the layer requirements in the following slide. The different layers and their requirements are as follows. The core layer has high bandwidth links. It connects the distribution layer devices to each other and the centralized resources such as database servers. The core layer consists of high-end switches. The distribution layer provides routing, packet filtering using access control lists, ACLs, and quality of service, QoS. Wide area network, WAN, access also occurs at this layer. Routers and Layer 3 switches are used here. The access layer is where end devices connect to the network, usually with a switch. Let us focus on an important Layer 1 and 2 technology, that is Ethernet, in the following slide. Today, Ethernet is a widely used technology for local area networks, LANs. It is a family of standards maintained by the Institute of Electrical and Electronics Engineers, IEEE. Ethernet is defined by 2 OSI model layers, Layer 1 physical and Layer 2 data link. Let us take a look at some Ethernet standards in the next slide. As seen in the diagram on the slide, IEEE Ethernet standards include the following typical LAN speeds and media. Ethernet includes the typical LAN speeds of 10 megabits per second, called Ethernet, 100 megabits per second, called Fast Ethernet, and 1 gigabit per second, called Gigabit Ethernet. The media under Ethernet includes copper cables, fiber, and wireless. Let us look more closely at Layer 1 Ethernet capabilities in the next slide. There are many physical layers in Ethernet standards. However, they use the same data link layer standards. The maximum length of a copper cable is 100 meters, about 328 feet for most standards. The standards listed for copper use unshielded twisted pair (UTP) copper cable, except for ThickNet. Following are the characteristics of Ethernet at the physical layer. The UTP cable used contains 4 pairs of wires. Only 2 of the pairs are used for Ethernet and Fast Ethernet. All 4 pairs are used for Gigabit Ethernet. Let us move on to the Ethernet in the next layer, that is, data link layer, in the next slide. The IEEE splits the Ethernet data link layer into 2 sublayers. The first layer, 802.3 Media Access Control, MAC, is responsible for data encapsulation and addressing. The second layer, 802.2 Logical Link Control, LLC, handles communication within layers 1 and 3. When Layer 1 bytes are received, they are framed and encapsulated into the Layer 2 datagram called a frame. When a Layer 3 packet is received, it is decapsulated. The Internet Protocol IP header is stripped, leaving a frame. Let us find out about a Media Access Control address in the following slide. The Media Access Control MAC address is the physical address of the Network Interface Card, NIC. It consists of 48 bits, 6 bytes, represented in hexadecimal digits. The first 3 bytes are the Organizationally Unique Identifier, OUI, that indicates the vendor. The last 3 bytes are assigned by the vendor. This address can be assigned, or it can be a burned-in address, BIA. A BIA is globally unique. There are no other NICs with this MAC address. We will discuss Ethernet frames in the next slide. Ethernet frames contain the following fields. Preamble provides synchronization. The start frame delimiter signals the beginning of addresses. MAC destination address is the destination of the frame. MAC source address is the source of the frame. Protocol type is usually the code for IPv4 hexadecimal 0800 or IPv6 hexadecimal 86DD. Data contains layer 1 bytes. 0 padding is added to meet the minimum 46-byte requirement if necessary. Frame check sequence, FCS, is used to check for transmission errors. Let us look at Duplex in the next slide. Devices communicate with each other using full or half duplex. With half duplex, only one device can transmit over the medium at a time. With full duplex, both devices can transmit and receive at the same time. Data collisions are possible with half duplex. This means the datagrams can collide with each other physically when being transmitted on the medium. When this occurs, the data is destroyed. Since frames transmitted on a hub are received by all attached devices, hubs cannot use full duplex. Switches and routers can use full duplex. However, this depends on the interface used for transmitting and receiving data. Some interfaces are limited to half duplex. When using half duplex, there must be a mechanism available to deal with collisions. This mechanism is dealt with in the next slide. To detect collisions in half duplex communication, carrier sense multiple access with collision detection, CSMACD, is used. This is a contention method. When a device has a frame to transmit, it monitors the medium until there is no activity. It sends the frame, but also listens at the same time. If the device detects other signals on the medium, there is a collision. When there is a collision, all devices transmitting at that time send a jamming signal. Then each device chooses a random amount of time before retransmitting. This is called the back-off time. Let us move on to the quiz section to check your understanding of the topics covered in this lesson.